When we are doing metamaterial simulation in CST, mainly for the reflection and transmission analysis, we know that there are two types of solvers available there, time domain and frequency domain solver. Each solvers has their own capabilities. So there will be lots of questions like will time domain solver supports the angle variation and polarization variation? What is the difference between time domain and frequency domain solver? So there will be lots of questions like this. So this video covers the difference between time domain and frequency domain solver and which solver we have to use when we have to analyze some particular sort of applications. This is the fundamental idea of metamaterial simulation. If we have a structure, we know that it is very long structure and the meshing will be huge and the simulation time will be huge. So the basic idea of the metamaterial simulation is like we will be considering only one unit cell. So unit cell is the basic structure which will be repeating along x and y axis to produce the entire structure. So in all the simulations, we will be considering only the unit cell of the periodic structure. That's we have to consider that every simulation is just the replica of the measurement. So we are doing the simulation to know the result before measurements. Like if you want to make some modification on the shape, periodicity, or anything, this simulation help us to understand that. So the simulation are the just replica of the measurement. So I'm just showing the measurement setup for a periodic structure. For a normal instance, both this transmitting and receiving antennas will be placed here, and this will be our periodic structure, and we will be taking the measurements. For angular measurements, we will be rotating these antennas along this arc and will be doing the measurement. For the polarization measurements, we will be rotating this antenna. A full length video about the measurement is also uploaded in our channel. So in case of a time domain solver, these are the boundary conditions we are using. That is, it uses electric and magnetic field boundary condition and a waveguide board. The concept behind this time domain solver is we are considering this structure is inserted inside a waveguide. So you can assume that we are going to measure the reflection property and transmission property of a unit cell by inserting this inside a waveguide. We know that the electric field distribution of the waveguide is along this direction. So that means along the y direction, this is the electric field direction, and this direction will be the magnetic field. So if you have to use the time domain solver, you have to know how this structure has to be put inside the waveguide. So if you are going to put it inside this thing, you know that along the y direction, you have to put the electric field, and along the x direction, you have to put the magnetic field. Otherwise, if it is like oriented 90-degree, these boundary condition has to be shift. So if you have to use the time domain solver, you have to know in which orientation the electric field is happening for the unit cell patch. That is the main condition to use the time domain solver. And here you know that when you insert the structure and you do the simulations, you know that we won't be able to make any changes on the propagation, like means we won't be able to make any changes like oblique incidence like this thing inside the waveguide. So it will be supporting only the normal incidence. And here also we know that the orientation of electric field is only one direction. Uh, that is only supported if we set these boundary conditions like this. That means that we will be getting only one polarization result from this time domain solver. So if you want to provide another polarization, we have to change this boundary condition. So I will show how it is done. So I said that using the waveguide board, it is supporting only one polarization. So I'm just checking what will happen if I am going to put mode 2 here. So we can check the orientation of the port using the 2D, 3D result and port modes. So I'm going to check the electric field orientation for the mode 1. Here you can see that the wave impedance is 376 ohm. That is our free space impedance. So, and it is showing mode type as TEM, and you can see the electric field orientation, which is same as whatever is happening inside the waveguide like this. So this shows the electric field orientation inside the structure. So here you can see that our mode 1 is supporting a particular type of polarization. So now I'm going to check what is happening for this E2 if I'm showing mode 2s here. So here you can see that for the E2 you can see it is showing TE mode, but here you can see that the wave impedance is not 377 ohm. So whatever the result you are getting from the port mode 2 is not acceptable to us, because we are considering a propagating electromagnetic wave, so its surface impedance has to be 377 ohm. So it is not desirable to consider mode 2 in time domain solver. So you have to consider only one mode for this time domain solver simulation. So if you want to change the mode of polarization in time domain solver, what you can do is you can just change this orientation. So now you have considered this electric field orientation. So for that you have put electric field along y-axis and magnetic field along x-axis. So if you inverse that, that is for the y-axis you are putting the magnetic field, and along x-axis you are putting the electric field, you can see that your polarization can be changed. This means that if you want to change the polarization, you have to change the boundary condition. So in this case, we can only expect, if we are providing a TEM wave, we will be getting only one polarization as output. So we won't be able to do any cross polar result analysis using this time domain solver. Only copolar result analysis is possible using the time domain solver. That's the beauty of frequency domain solver. By using the frequency domain solver, all these disadvantages are gone. So let's see how it is done in frequency domain solver. The main advantage of frequency domain solver is it supports oblique incidence and different polarization. Why it can support these things are, this solver is based on Floquet theory. So Floquet theory state that if we have a periodic structure and if we want to find the electric field on a cell, it depends upon the electric field on the reference cell by a phase shift. That is this expression which shows that electric field on any cell, that is Ex plus A, where A is the periodicity, is related to that reference cell by a phase shift. So this forms the basic idea about the Floquet theorem. So in this case, we are not considering the structure is not inside any waveguide or nothing like that. We are considering there is a plane wave excitation on this structure. So for this we are using the boundary condition unit cells, and you can use the Floquet boundary condition. So in this case, using the Floquet boundary condition, we can provide two modes here. The first mode will be means it will be representing the TE mode where electric field is oriented in this direction, and the second mode will be along x-axis in this direction. So we can have both the polarization results using the frequency domain solver. So I'm just showing how the polarization is oriented for these modes. So if you check the electric field orientation for the mode 1, you can see that it is showing TE, and you can see the wave impedance as 377 ohm. And for the mode 2, you can see it's showing TM, and the wave impedance are 377 ohm. So both are showing the free space impedance, and both are showing different polarization. So here you can see the electric field orientation along this direction, and you can see the electric field orientation along x direction. So using this frequency domain solver and two port modes, you can get the result for copolar and cross-polar result. So you can use this S parameters for analyzing copolar and cross-polar result. And if you want to measure the angular stability, you can always also use this theta and phi parameters, and you can vary these parameters for the angular measurements. So in this video, I have explained about T and TM modes. So you can watch that video. It will be useful. Thank you.